Okay, so think about this. For almost all of history, our picture of the universe was, well, tiny. We thought we were it, the center.
A pretty static, unchanging place.
Exactly. But then, over the last century or so, everything changed. Completely. We found out we're in this huge, expanding cosmos with billions of galaxies. How did we even figure that out? That's what we're getting into today.
Yeah, it's an amazing detective story, really. We've been looking at this comprehensive review that lays out all the big discoveries about how the universe started and evolved.
Like the highlight reel.
Pretty much, yeah.
Yeah.
The highlights of a century of mind-blowing cosmic discoveries. How we went from like one galaxy to, well, everything we know now.
Okay. And this review hits everything, right? Big Bang, inflation, dark matter, how galaxies formed, the work.
It covers a ton, yeah.
Yeah.
Based on loads of studies, observations. We're trying to pull out the really key stuff, the most fascinating bits for you.
So where does this whole revolution start?
Well, you could say modern cosmology really kicks off with Einstein, 1917. He applies general relativity to the whole universe.
Which was basically just the Milky Way back then, in most people's minds.
Exactly. And to even do that, he had to make a big assumption, that the universe, on the grandest scale, is basically the same everywhere. No special spots.
The cosmological principle, we're not unique.
Right. The Copernican idea, basically.
Yeah.
But Einstein hit a snag, didn't he? He thought the universe was static.
Yeah, unchanging. But his math didn't quite agree.
No, it didn't naturally lead to a static universe. Gravity should make it collapse.
Yeah.
So he kind of forced it. He added this thing, the cosmological constant.
Ah, fudge factor.
Well, yeah, sort of. It was like an anti-gravity force to keep things stable. But even that model wasn't really stable. And interestingly, the same year, de Sitter found another solution.
What was that?
An expanding universe. Exponentially expanding, actually, which years later becomes super important for inflation theory.
Wow, so the idea of expansion was there right at the start almost.
Kind of bubbling under, yeah. Then in the 20s, Friedman and Lemaitre, they weren't stuck on the static idea. They found expanding solutions independently.
Okay.
And then Robertson and Walker, they developed the math, the metric, to actually describe the geometry of a universe that's the same everywhere and in all directions. Homogeneous and isotropic.
Got it. Like the mathematical rules for that kind of universe.
Exactly. It gives you a framework.
So the theory was building, but what about actual evidence? What did we see that suggested expansion?
Okay, yeah, observations. This is where Vesto Slipher comes in, starting way back, like 1912. He was looking at these spiral nebulae.
Which we now know are other galaxies.
Right. But back then, that wasn't clear. He noticed the light from most of them was redshifted.
Meaning they were moving away from us, like a siren's pitch dropping?
Precisely. Redshift means moving away. Though interestingly, a few were blue-shifted moving towards us, like Andromeda, our neighbor.
Okay, but maybe they were just drifting around locally.
That was the question. But then, building on those expanding universe models, Lemaitre and Robertson actually derived Hubble's law, the idea that velocity is proportional to distance. V equals h0r.
They figured that out from the theory.
They did. But Edwin Hubble, in the 1920s, he's the one who really nailed it observationally. He used Henrietta Leavitt's work on Cepheid variable stars.
Ah, the standard candles. Stars that pulse at a rate related to their brightness.
Exactly. They let you measure distance. And Hubble used them to show definitively that these nebulae were way outside the Milky Way. Other galaxies. Game changer. Opie had suggested it earlier, but Hubble proved it.
And that confirmed the redshift distance link?
Yes. Hubble, with a lot of help from Humason on the observation side, showed that the more redshifted a galaxy is, the farther away it is. Z equals h0r.
Okay.
Now, technically, that's an approximation of the velocity-distance law. Works best nearby.
Yeah.
But the implication is huge. Distant galaxies are receding incredibly fast.
So fast that beyond a certain point, the Hubble distance, they're moving away faster than light.
Seems like it, yeah. But it's not the galaxy moving through space faster than light. It's space itself expanding and carrying the galaxy with it.
Mind-bending. Okay, so if space is expanding, going back in time means...
Everything was closer together. Much smaller, much hotter, much denser. The early universe.
And that's where the first elements came from.
That's the idea. Big Bang nucleosynthesis. In that incredibly hot, dense soup, protons and neutrons fuse together.
Making what? Helium?
Things like deuterium, that's heavy hydrogen, helium-4, a bit of lithium-7, the light elements. And the amazing thing is, the amounts predicted by the theory match what we observe today remarkably well.
Wow. That's strong evidence.
It really is. Gamow pointed out early on that these reactions happened fast, but only for a short time as things cooled. So you couldn't just assume equilibrium.
Right, it was a quick burst of activity.
Exactly. And Alpher and Herman took it a step further. They realized this hot phase should have left behind radiation, an afterglow.
The cosmic microwave background?
Yep. They even predicted its temperature, roughly, which is pretty credible.
So they predicted this echo of the Big Bang.
They did. And it also became clear that this early nucleosynthesis only makes light elements. All the heavier stuff, carbon, oxygen, iron, everything else, that comes from stars later on. Exactly. Forged inside stars and in supernova explosions. Oh, and the amounts of helium and deuterium are super sensitive to how much ordinary matter, baryons, there was back then. So it gives us a way to measure the baryon density.
Clever. Okay, so back to this predicted afterglow, the CMB, often called the smoking gun.
It really is considered that by many. Funny thing is, there were hints before it was properly found. McKellar saw its effect on molecules back in the 40s.
No way.
Yeah, and Penzias and Wilson at Bell Labs in the 60s, they found this annoying background noise in their antenna.
And it turned out to be the echo of creation.
Pretty much. Talk about serendipity. But the first papers really discussing it came from Zeldovich's group in the USSR and Dick and Peebles at Princeton around 64, 65.
Ah, okay.
Then Penzias and Wilson made their measurement public, and Dick's team immediately said, that's it. That's the Big Bang afterglow.
And this CMB is everywhere.
Everywhere, filling the entire universe. It's actually the dominant radiation, about 400 photons in every cubic centimeter of space, at just under 3 Kelvin.
And its spectrum, the pattern of its light.
It's a near-perfect black-body spectrum, exactly what the Big Bang predicts. The Kobe satellite measured this with incredible precision.
That must have been huge for the Big Bang theory.
Monumental. Basically killed off competing ideas like the steady-state theory.
And Kobe found something else too, didn't it? Tiny temperature differences.
Yes. Anisotropies. Tiny hot and cold spots in the CMB map, just millionths of a degree difference.
And those are important because
They're the seeds. The primordial lumps and bumps in density that gravity later grew into all the galaxies and clusters we see today. Without them, the universe would just be smooth gas. There's also a bigger pattern, the dipole, from our own motion through the cosmos.
Okay, so it's an amazing picture built up piece by piece. But it wasn't all smooth sailing. Were there problems with this simple Big Bang idea?
Oh, absolutely. If you just run the clock back naively, you hit a singularity. Infinite density, infinite temperature. Our physics breaks down.
Right. The very beginning is still fuzzy.
Very. And other puzzles emerged, like the horizon problem.
Why is the universe so uniform?
Exactly. How can regions of the universe that were seemingly never in causal contact light, never had time to travel between them, have almost exactly the same temperature, like we see in the CMB? Alpher noticed this early on, too.
It's like they talk to each other somehow.
Yeah, but they couldn't have. And then there's the flatness problem. Why is the universe's geometry so incredibly close to Euclidean flat?
And the proposed fix for these headaches is inflation.
Inflation, yeah. This idea of a period of absolutely mind-bogglingly rapid exponential expansion, like way less than a second after the Big Bang.
Driven by some kind of energy field?
A hypothetical scalar field, the inflaton field. This massive stretching could take a tiny, smooth, connected patch and blow it up to enormous size, explaining why the observable universe looks so uniform and flat today. It solves the horizon and flatness problems.
Wow. Okay.
And maybe the coolest part, tiny quantum fluctuations during inflation would get stretched too, becoming the seeds for large-scale structure. Inflation naturally generates those initial ripples.
It's like one idea solves multiple huge problems.
It's very compelling for that reason, which kind of brings us towards the more recent stuff, the invisible universe.
Dark matter and dark energy. The elephant, or rather the vast empty space, and the invisible elephant in the room.
Exactly. Most of the universe, it turns out. Evidence for dark matter goes way back to Zwicky in the 30s. He looked at galaxy clusters.
And saw galaxies moving too fast.
Way too fast. Faster than the gravity from the visible stars and gas could hold them. Something invisible had to be providing extra gravity. Smith confirmed it later in Virgo.
And the leading idea is cold dark matter, CDM.
That's the standard model, yeah. Slow-moving, non-interacting particles that clump together and provide the gravitational scaffolding for galaxies to form.
Okay. And dark energy, that's different again.
Totally different. That's this stuff causing the expansion of the universe to speed up.
Which we found out from supernovae.
Type Ia supernovae, yeah. In the late 90s, 2 teams found distant ones were fainter, meaning farther away than expected in a decelerating universe. The expansion is accelerating.
Wow. So something is pushing things apart.
Or pulling space apart, yeah. We call it dark energy. Could be Einstein's cosmological constant making a comeback or something else entirely, but it makes up like 70–75% of everything in the universe.
The dominant component.
By far.
Ah.
And that number lines up with what we need to explain the CMB patterns and the amount of structure we see.
So gravity's pulling things together, dark energy's pushing them apart, a cosmic tug of war.
That's a good way to put it. And how structure forms depends on that balance. Gravity amplifies those tiny initial ripples from inflation.
The gene's instability idea?
Sort of, yeah, but modified for an expanding universe. Gravity makes dense regions denser. But as dark energy takes over, it starts to slow down and eventually stop the growth of the very largest structures.
So the expansion history dictates how structure grows.
Absolutely. After the CMB formed, when light and matter decoupled, ordinary matter started falling into the gravitational wells already created by dark matter clumps.
Leading to the bottom-up formation. Small things first.
That's the picture in CDM, yeah. Small dwarf galaxies form, then merge over billions of years into bigger galaxies, then clusters. Hierarchical formation, not the old top-down ideas.
And we can actually see this large-scale structure, this cosmic web.
Oh, yeah. Massive galaxy surveys, like Sloan Digital Sky Survey, SDSS, 2DF, they map millions of galaxies in 3D.
Measuring their positions and redshifts.
Exactly, revealing this incredible network of filaments, walls, and voids. We also use clusters and quasars as beacons tracing the structure. And measuring peculiar velocities, how galaxies move off the perfect Hubble flow, tells us about the underlying mass distribution, including dark matter.
How do you analyze all that data?
Statistically, we measure things like correlation functions, how likely galaxies are to be near each other, and power spectra. And a really key thing we found are baryon acoustic oscillations, BAO.
What are those?
They're like frozen sound waves from the early universe. Before the CMB formed, pressure waves rippled through the plasma. They left a characteristic scale, a preferred distance between galaxies, imprinted on the matter distribution.
Like a standard ruler built into the cosmos.
Exactly. We can use that scale to measure distances and the expansion history.
So putting it all together, supernovae, CMB, BAO, clusters, lensing.
It all converges. Multiple independent lines of evidence all point towards a consistent picture. A flat universe, accelerating, dominated by dark energy and cold dark matter. The ACDM model, lambda for dark energy, CDM for cold dark matter.
That's what they call cosmic complementarity. Different methods checking each other.
Precisely. It helps break degeneracies in the data and gives us much tighter constraints on the cosmological parameters.
Yeah.
Hubble constant, matter density, baryon density, etc.
It really is just an incredible story, a century of discovery that completely overturned our view of, well, everything.
It's been truly revolutionary, from thinking our galaxy was the universe to mapping this vast, evolving cosmos back almost to its beginning.
But, as always in science, there are still questions,
Yeah,
right? Big ones.
Oh, absolutely. We've built this amazing model, CDM, and it works incredibly well. But we still don't fundamentally know what dark matter is, or what dark energy is.
The two biggest parts of the universe are mysteries.
Pretty much. And why is there matter but hardly any antimatter? The baryon asymmetry problem. What exactly happened during inflation? These are huge open questions.
So we've learned a massive amount, but the journey isn't over.
Not by a long shot. But think how far we've come in just 100 years. It's been breathtaking. And the potential for future telescopes, future experiments, who knows what revolutions are next.
Keeps you wondering, doesn't it? Maybe this deep dive has got you thinking about those cosmic mysteries, too. There's definitely more out there to explore.